An exponential function is a nonlinear function. Okay, nonlinear, what I mean by that is that when you graph it, it's not a line. Okay, in other words, you do not have a constant rate of change. And this function is going to be in this form. Y equals a times b to the power of x. Okay. So linear functions, like I was saying up there, have this constant difference or this constant rate of change. When you look at a table, what you see is that you are either adding or you're subtracting some constant value over and over again. Like you're adding 2 each time, or you're subtracting 5, or something like that. In an exponential function, you don't have that constant difference. You have something called a constant ratio, which is a number that you're not adding every time. Instead, you're multiplying every time. Or dividing, but usually we can talk about anything that's going on with division as multiplication. So one of the types of questions that I'm going to be asking you is, like, if you look at a table, tell me, is this exponential or is it linear? Okay. Now the way that you'll be able to tell if it's exponential or linear is based on how the y value is changing. So if you're adding some constant amount every time, or you're subtracting, if there's a constant difference, we say it's linear. You know, like if it has a constant rate of change. If the rate of change is not constant, then we want to check to see if there's some constant multiple, right? Some constant ratio that we're multiplying by to get from one step to the next. And if that's the case, it's exponential. Now, it might be the case where it's actually neither, where you're not adding or multiplying anything, and it's just sort of random, or seems like we don't know what the pattern is yet. So, like number 1, we can kind of look at this as being either, okay, so I'm subtracting 4, subtracting 2, and then subtracting 1. So my first question is it linear? Once again, since the amount that I'm subtracting by or adding, is not the same, we say it's not linear. Okay, so the next check is to say, okay, well, it's not linear, but is it exponential? Is there a ratio that I'm multiplying by every time? Is there some constant multiple? So what do I need to multiply by to get from 8 to 4? I need to multiply by 2? By a half, right? Yeah, 8 times a half, or you could say 8 divided by 2, I guess. That'll work. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. So do we have a constant ratio? Are we either multiplying or dividing by the same thing? Yes. So that means that this table is exponential, or shows an exponential relationship. So yeah, with all these tables, you want to be doing those 2 checks. Like, is it linear? Is it exponential? So number 2, I say, okay, first, is it linear? Well, I'm adding 4, followed by adding 8. I shouldn't have to go any further, right? Is this linear? No. There's not a constant rate of change. Right? So I know it's not linear. Let's check to see if it's exponential. Now, how do I go from 4 to 8? Times 2, right? So times 2 will get me to 8, times 2 will get me to 16, times 2 gets me to 32. So is the ratio constant? Am I like multiplying or dividing by the same number? Yeah, so we say this is exponential. Look at number 3. Let's start by checking to see if it's linear. I'm going to add 2, add 2, add 2. So right away, I can see that the rate of change is constant. Right? I'm adding the same number every time. So this is linear. Once you figure out what it is, you don't have to check anything else, because it can't be both linear and exponential. So once you've decided that it's one versus the other, you're done. So if we look at 4 through 6, all we're doing is practicing evaluating these functions. So I'm given a function like y equals 3 to the x, and I want to know what is the value of this function. In other words, what is the y value when x is 5? So this is going to be purely a calculator problem. You're just going to type this in and see what you get. What this is really asking is, when x is 5, what is y? So what's 3 to the 5th power? What is it? 243? So that's like 3 times 3 times 3 times 3 times 3. Okay. Number 5. We want to know what's 1/4 to the 3rd power. Now with fractions, whenever you raise them to a power, remember that one of our properties says we could just raise like both the numerator and the denominator to that power. We could do them separately. So for instance, 1 cubed is just 1. Well, what's 4 cubed? 64. Yeah, so we get 1 over 64. For number 6, we're going to substitute 4 into x. So we get y equals 3 times 4 to the 4th power. It's going to be probably a decent sized number here. $768? Okay. That sounds about right. Okay, so that's, we want to be able to look at these relationships either like we're looking at them as an equation, we're looking at them as a table, but anytime we're talking about functions, one of the big things we talk about is how to graph these things. So there are a few different components to the graph, and we'll get into how to find all those things, but first there's a few new words that we need to define. So the first one is something called an asymptote. Okay, so an asymptote is a line that the graph is going to approach, but it doesn't actually cross over it. It doesn't actually touch it, at least not for our purposes. So, in other words, as x goes to either infinity or negative infinity, as you look to the left or to the right on the graph, at least one of those sides, your graph will approach some horizontal line. And we'll see how that actually plays out when we start to graph it. When you have exponential functions, as long as you don't have some negative sign in front of it, it's gonna fall into one of two categories, either growth or decay. So these two words are going to sort of describe the exponential relationship. When you have exponential growth, that occurs when the quantity increases by the same amount from left to right over time. So let me make a little note from left to right. Just like how you would read a book, right? You read a graph from left to right. So if the graph is going up, if it's increasing, we call it growth. If the graph is going down, we're going to call it decay. So either like it's growing or it's decaying. It's either getting bigger or it's getting smaller. So it's decay when the quantity decreases from left to right. So when you have I'm just going to do a quick sketch because you want to start to get an idea of like what these exponential functions look like. We know what a linear function looks like. It's just a line. But you also want to have an idea of what these exponential functions are going to look like. So when you have growth, it's going to look basically like this. You'll have your x and y axes, and your graph is going to kind of go along the x-axis and then kind of shoot up like that. So it's going to grow. And then for a decay, for exponential decay, instead of going up, it goes down. So it's like you have this graph, but reversed, where the increase is to the left and it decreases to the right. So let's practice graphing a few of these. Remember that you're going to have your calculator, so make sure you're using it. Like, you can graph these by hand, yeah, but why would you? You know, there's no reason to. All right, so I'm going to give you just a few tips on how to graph these. Number one tip, use your calculator. Okay, go to y equals in the calculator, type in the equation, and start getting values from there. Don't try to do everything by hand. Now, when you have a blank table like this, usually it's a good idea to pick values that are going to be on your grid. So this is not like you have to pick these values, but what I usually default to is just going from like -2 to 2. And that'll usually give you a good idea of what's going on. Now, depending on how many blanks your table is, you might have to go a little bit beyond that, but that's where I usually start with. So I'm just going to list my x values as -2, -1, 0, 1, 2. It looks like we have one extra little piece, one extra little row, so we'll throw in a 3. So we want to graph y equals 2 to the x. Now, some of these you could probably get in your head pretty easily, like what's 2 to the 0th power? It's 1, right? What's 2 to the first power? 2. What is 2 squared? 4. So, and you can keep doing that. You don't have to know all those, off the top of your head. Like I said before, let's use a calculator. You want to save time and be more accurate. There's not a whole lot of downside to doing it this way. So in your calculator, and just look on with somebody or do this on your own, is press y equals. This is where you're going to type in your function, and we just want 2 to the x. So all right, 2 to the power of x. And so make sure you're using this little button for x. Now, if I hit graph, you'll get an idea of sort of what the graph is going to look like. It looks like an exponential growth graph, but we want to be a little bit more accurate about it. We don't want to just do like a sloppy curve. We want to actually plot points. So to get that table on here, you hit second graph, and that'll bring you to the table. Now, it's possible that not all of these points are going to fit on the graph. The way exponential functions work is they grow like really, really quickly. So if that growth occurs like inside your table, you're going to see that we're going to grow like too big. It's not going to fit on the grid. That's fine. Not every point has to be on the graph. But let's fill out the table here. So when x is -2, y is 0.25. Oh, let's see. Let's pull that up so you can actually see it. There we go. When x is -1, y is 0.5. Let's double check the ones we did by hand. 1, 2, and 4 look good. And then we have 3, 8. So like I was saying before, like this last one's not going to fit on there. That's okay. You just fit what you can. So let's plot all of those points. -2, comma, 0.25. So it's just going to be barely above the x-axis. -1, comma, 0.5. 0, comma, 1. 1, comma, 2, 2, comma, 4, and 3, comma, 8 would be like way up here. So the graph is going to do this. Any questions about how we came up with any of those points? All right, well, now that you have that graph, let's analyze this graph a little bit. What does it appear that the y-intercept is? 1. So 0, 1, that's our y-intercept. Our domain is all of our possible x values. Now, are there any x values that we're sort of not allowed to plug in here for any reason? Like is 2 to some power ever undefined? No, it's always going to be defined. So for all of these exponential functions, the domain is always going to be all real numbers. The range. So this is not going to be all real numbers. Can you see like where the graph sort of will never go below? Like, is there a limit to how small this graph can be, or the values of this function can get? Like, as I go to the left, what do you notice happening with the graph? It's what? It's going down, right? But it's sort of not going down like a lot. Like after a while, it's getting smaller. You know, little, like the increments that it's decreasing by are getting smaller and smaller. And what's going to happen is this will never actually get to 0. It'll always be a little bit above 0. Because if you think about it, like as you could scroll back in this table, and the rounding might look like it eventually goes to 0, but it will not. You actually get these really tiny numbers that are going to be very close to 0. You never actually get there. So the range, unless you have a reflection or something like that, the range for all of these exponential functions will be y greater than 0. So all the points will be above the x-axis. And that's because we have something called an asymptote for these exponential functions. So these asymptotes are lines that this graph won't ever cross. So you could probably graph the line that it won't cross. Right? I'm just going to use a highlighter to do that here, just to show it off. Is this line right here? Right? It won't cross the x-axis. So what's the equation for that line? Y equals 0. Does this graph show growth or decay as you read it from left to right? Is it getting bigger? Is it getting smaller, essentially? Yeah, bigger, right? So it's showing growth. So these follow-up sort of analysis questions are mostly going to be answered in the same way every time. So it'll just take practice, like kind of doing it over and over again, so that it becomes sort of second nature to you. So you sort of already know what the answer is going to be before we start. Any questions about that whole first graph? All right, so let's try number 2, or I'm sorry, number 8. Let's work on the table. I'm going to use those same x values, -2, -1, 0, 1, 2, 3. I'm going to go to my calculator, clear out the last equation, and type the new one in. 2 times, and I'm going to put in the fraction as alpha y equals, enter, 1/2, close the parentheses, to the x power. All right, so once you get it in, put it in. We're going to look at the table and start filling it out. So I'm going to do second graph. Oh, I had scrolled up way up on the last one, so I need to go back down to get the values I need here. There we go. So at -2, y is 8. At -1, y is 4. Then we got 0, 2, 1, 1, 2, 1/2, and 3, 1/4. So now let's start plotting all those points, or as many as you can fit. Right? You can't fit -2, 8 on there. That's okay. Don't worry about it. Just fit the ones that actually that you can. -1, 4, 0, 2, 1, 1, 2, 1/2, and 3, 1/4. All right. So there's your exponential function. Our asymptote is in the same place, and it will pretty much always be in the same place. I don't think I'm going to give you any, at least for now, where the asymptote is not the x-axis. So that'll be pretty consistent. What's the y-intercept? 2, right? So we'll write it as a coordinate, 0, 2. What's the domain? So y is greater than 0 is correct for the range. The domain is going to be all real numbers. I heard somebody say that too, but and that's going to be every time all real numbers for the domain on that. That answer will always be the same for exponential functions and linear functions for that matter. The range here, y is greater than 0. Right? It's above the x-axis. We're going to see the next one is going to not be above the x-axis, so I'll show you how to write that as well. The asymptote is going to be the same line like every single time, like unless something weird happens, but I don't think that will for you. Y equals 0. And does this display growth or decay? Decay, right? Because from left to right, the values are decreasing. All right, our last one for today. Number 9. Let's fill out the table. -2, -1, 0, 1, 2, 3. Now something that's different about number 9 compared to the rest is that we've got this negative sign sort of stuck out. We got a -2 as our a value. So that's going to change the graph's look a little bit, and we'll see why that is. Go ahead and hit y equals. And let's type in the equation here. -2 times 3 to the x. We'll go look at the table. So I'm going to have to round some of these decimals. -0.22, or it looks like it's just 2 repeating. And then -1 comma -0.6 repeating. It says 667, but I'm going to just chalk that up to rounding. 0 comma -2, 1 comma -6, 2 comma -18, and we're really getting into numbers that we're not going to be able to graph anyway. -350, -54, or sorry, 3 -54. So now we plot all these, and then we get to play connect the dots. -2 comma -0.2, -1 comma -0.6, 0 comma -2, 1 comma -6. I'm going to at least try to put that on there. And then I'm not going to bother with the rest. So it looks like our exponential function is doing this. All right, notice that our asymptote, even though this is on the negative side of the graph, like it's on the bottom half, it still has an asymptote at y equals 0. So that still hasn't changed. So let's run through all these questions. What's the y-intercept? -2. So we've got 0, -2. The domain is still all real numbers. Now the range will be a little different than the last two, right? Because this function is below the x-axis rather than above it. So how will we state the range? All right, the previous two we had y is greater than 0 because all of the points had positive y values. Yeah, y is less than 0. Yeah, it's just going to be the opposite statement, right? Instead of the function values being above 0, the function values are below 0. The asymptote, though, is still the same, y equals 0. Now, so this is kind of weird. When we talk about growth and decay, typically we're talking about functions that look like number 7 and number 8, where they're above the x-axis. So if you have a negative coefficient to your exponential function and your graph's down here, we're actually going to say that it's neither growth or decay. It doesn't really fit neither. It doesn't fit either of those.